Hi, everyone. Welcome to the webinar, and thanks for joining us. Not just welcome to the webinar, but welcome to the RBR offices here in Ottawa, Canada. So this is our head office, and we do everything here. It's an active manufacturing facility. We have our Cal labs. We do our R&D. We do our technical support. Support team lives here, as well as all of our marketing and sales are headquartered here. So this is where all the action happens. Now, I want to introduce myself. My name is Rob Lee, and I'm the Director of Marketing here at RBR. And I'm going to help guide you through this process. So one of the big questions that comes up is, why calibrate? And the short answer is that to maintain datasheet accuracy, we recommend annual calibration. Now, the fact is, sometimes we understand the logistics of getting that done can be challenging, and that's why we introduced our 3-year free calibration guarantee, which takes some of the questioning out of how long it's going to take to get calibration done, because we guarantee 3 weeks or less on standard calibrations for a turnaround time. So today we're going to see how a CTD goes through the calibration process and the elements that are involved. And I'm going to be turning it over to the experts soon, but just a couple of comments about how this is going to work. So we're in an active manufacturing area. We're live. The Cal lab is operating right now, live. So we might get interrupted with a few things, but that's just part of the game. So the other thing is we've got quite a few attendees on. So we're going to do our best to get to questions. I'll probably wind up covering some of the more common ones as we walk through. And then we'll commit that we'll get back to you and answer your questions specifically. And we recommend you put them in the Q&A. And then we'll try and curate some of the more popular ones as well, so that we can send them out so you can see what other people are asking as well. All right, with all of that done, let's get started. So when a CTD or any instrument for that matter comes in, the first stop is the service team. And I'm going to introduce Mark Stacy, our tech support manager, to start explaining this part of the process and what happens to the CTDs when they come here.
Great. Right. Thanks, Rob. So as Rob says, this is the service bay we have here. As the instruments come in, they go through 2 stages. First one is receiving. The second one is triage. So when the instruments come in on receiving, what we do is we check all of the serial numbers that come in on each work order, each RMA. We'll document the additional sensors, the cables, the cages, and any sensor guards that come in as well. This is to make sure that what comes into the factory actually leaves the factory after all of the work is done. The instruments get placed in a plastic box, and that helps them stay together. That helps everything stay protected as they move through the factory and go from the service bay here into the calibration lab, where you'll be shortly. So that's the first stage, that's receiving. Second stage is triage. Now, this is a full suite of tests that we do on every single instrument that comes through, whether it's coming in for repair or whether it's coming in for our 3-year free calibration guarantee. So what we do, we check the connections, we connect the instrument up to Ruskin, just the same as you would do at your shop. We'll check that the data is streaming and within tolerance. We'll check the twist activations, we'll check the connectivity. And what we'll do is we'll take the instrument apart. We'll check that the sensor end cap is working. We'll check that the housing is in good condition. And we'll check all of the electronics. So we'll do current checks, we'll do connectivity checks to make sure the instrument is doing exactly what it should be before it goes off to calibration.
That's excellent. It's a great explanation. So we can actually detect things that are going on with the instrument, even if the customer doesn't necessarily know there's something wrong.
That's right. So an instrument may look great from the outside, but sometimes on the inside, because of the harsh environment that the instruments are deployed in, sometimes there's something else going on. And really, it's that multi-point standard check that ensures that your instrument is going to leave the factory in a tip-top condition for your research and for your data collection.
So what happens if we do identify that something's wrong at that point?
Yeah, that happens occasionally. When instruments come in on calibration, the 3-year free guarantee, depending on the channels and depending on the configuration of the instrument, is assessed and confirmed. However, as you say, if we do find something that needs repair, if we do need something that needs attention, whether that's those external sensors, whether it's the cables, whether it's the electronics inside, we'll provide you with an assessment report that details everything that the instrument needs. And we'll ask you to approve that. We'll supply a quote before we do any of the work, before the instrument goes into the calibration lab.
Excellent. All right, great. That's a great introduction. So now let's keep the process going. And with that, we're going to wander over here. And we're going to introduce Ariel Wainwright. And Ariel is our calibration manager. And so Ariel is going to walk us through the next stages. So where are we going now?
So now we're going to the calibration lab where all the instruments actually get put through.
Awesome.
And we're, yep,
Yeah, so we put all the instruments through here.
100% of the instruments go through the calibration.
So that
laboratory.
includes production units. That includes production units. It includes anything coming
service
out.
units, repair units, anything that comes through the door actually goes through the entire process.
Excellent. Okay, so what parts of the process are we going to see?
So since we're talking about a CTD, we'll actually be looking today at temperature calibration, pressure calibration, and conductivity calibration. So
Perfect.
all three main areas of the instrument.
All right, well, let's head over to temperature.
All right. So just follow this way here.
All right, we're a little tight in this one, so
Yes.
I'm going to let you squeeze in there.
Absolutely.
And let us know what's going on.
So Jim, if you can just. So yeah, I just asked June to move a little bit because he's going to help us out with the. In a little while, I'll get to show you the triple point of water cell that we actually use to do our verifications. So we'll get to that in a minute. Let me just start by explaining more or less the overall process. So once a unit is received, either from production or from the service department, as Mark was explaining, the first step of the process would be to put the instrument through our temperature calibration. We do an 8-point temperature calibration throughout the range of -5 degrees Celsius to 35 degrees Celsius. And the way we accomplish that is by immersing each instrument in our fluid baths. In this case, we're using Hard Scientific 7035 baths, if I'm not mistaken. Here we see one example of it, which is currently close to 0 or -5 degrees. So what would happen is we would actually take your instrument, immerse it in this fluid bath, and then start the 8-point calibration cycle. The cycle typically takes around 10 to 12 hours. We do a 1-hour plateau for each one of those temperature points. So we typically, typically the cycle is about 1 hour, which is enough for equilibrium and stabilization time for both the instrument under test as well as our reference standard, which I will talk to you about now. So the reference standard that we use is an SPRT, or a standard platinum resistance thermometer. We have 2 models right now, but mostly we use our Isotech 670 SL models, which are metal sheathed SPRTs. And the way it works is we basically introduce our reference standard as close as possible to the marine thermistor, and then we start the 8-point cycle that I just spoke to you guys about. Once the entire cycle is finished, we then use Ruskin, which is our in-house developed calibration software, to actually process all that data, create the best fit polynomial for that, and adjust the instrument as per the reference readings that we obtained from our reference thermometers. I do want to mention that we do our own verifications and or calibrations of our reference thermometers in-house in order to assure that we have instruments or reference instruments that are maintained within their accuracy tolerances. So the way we do this is we perform 2 primary realizations that are basically, the endpoints of that range that I talked to you about, -5 to 35. So we do a triple point of water realization, which is 0.01 degrees Celsius, as per an international convention that's called the ITS 90, or the International Temperature Scale, which is an international convention that recognizes certain melting points of certain elements. So the triple point of water is 0.01. I don't know if you can actually see that with the camera. It's right there. And then for the upper limit, we use the gallium melting point. So we also have a gallium cell for that. And we typically do, or not typically, I should say, we actually do a verification in the triple point of water cell on a daily basis. We actually have 2 triple point cells, so we're constantly verifying in both cells. And we do the gallium verification once a month. So without further ado, let me now do a proper introduction of June. This is June, our calibration engineer. He hails from China, where he served for over 8 years at the National Center of Ocean Standards and Metrology. And June joined us about roughly 2 or 3 years ago, I want to say. And now June can show us what a triple point cell looks like, which is where we verify our standard reference thermometers. So this is a dewar where we keep our cells conditioned. For those of you that have never seen this, this is what a triple point of water cell looks like. So water is actually living here in its 3 natural phases. So we're talking about its liquid phase, its solid phase, and its gas phase. And when the triple point is correctly realized, we actually have a mass of ice that can just circle around the center tube, which is where we insert our SPRT. Okay. Yes. I don't know if you can, if the camera can actually come in here, but you can actually see the ice is suspended around the core. And it's actually spinning as June revolves the cell. Okay, thank you, June. So moving right along, we'll now go to our pressure calibration area. Join us.
Awesome. So we did get one question live over the chat, and just another confirmation about how often CTDs should be calibrated. And as I mentioned earlier, like to maintain data sheet accuracy, we recommend annual calibration, so once a year. So where are we going to?
So we're going to pressure calibration.
Excellent. Let's do it.
So moving right along. So this is where we actually perform our pressure calibrations. And the way we do this is we actually immerse our instruments into these pressure vessels, depending on the pressure rating of the instrument. And we run each instrument through a 10-point, typically a 10-point pressure calibration cycle. So if an instrument has a pressure rating of, let's say, 2000 dbar, typically we'll run 10 plateaus that are evenly distributed across the entire pressure range of the instrument. We, in order to confirm hysteresis, we actually do an increase in pressure, and we also depressurize. And the actual calibration points between our reference standard, I should say the measurements that are taken between our reference standard as well as the DUT are actually taken during the depressurization cycle. So that's when we actually plateau, stabilize, and take our readings for the 10 different points. So basically we have an ambient temperature pressure vessel. We run our units firstly through our warm pressure vessel. And once the unit has undergone these 10 temperature points, we then run them. We then run the unit through a cold conditioned pressure vessel, which is typically in the order of 2 degrees Celsius. The reason we do both temperatures is to actually calibrate the instrument to compensate for temperature dependency. So we do pressure correction off of temperature. So yeah, so the instruments are actually immersed in these tanks. In terms of like, the reference standards that we use, you can see 3 of our reference standards for these pressure levels. I should note that these pressure vessels can only go up to 2000 dbar, rated for that pressure level. So right now we typically use these 2 pressure controllers that are located here at the bottom. These are Menser CPC 6500 pressure controllers. And we have nitrogen cylinder gas, which is utilized by the pressure controllers in order to pressurize the vessels at the different plateau points. We can actually see that one tank is running right now. This is color coded, so this green hose means it is actually running the CPC 6000 pressure controller at the moment. And right now, it's at basically 1 ATM. So it might be just starting off the complete pressure cycle. So we always start off at 1 ATM, or it might be finishing pressure cycle. Based on this reading here, I can see that we're actually starting the pressure cycle for this unit. So there is a stabilization period at 1 ATM, and then we start actually pressurizing at the other levels. So yeah, so we have these two tanks. We actually have a larger diameter tank in order to fit, larger units, such as OEM floats. We also do some pressure testing, which is what we call bladder testing, which is where we confirm pressure dependency on the conductivity of the cell, which I believe that might be a source for another webinar, but just wanted to show you guys what this tank is used for. And if you can just follow me over this direction. This pressure vessel is where we test all our high pressure instruments. High pressure meaning above 2,000 all the way up to 10,000 dbar. This system works a little different than the previous system that I showed you. This one actually works with shop compressed air, and we actually have an in-house developed system working with a compressor. And over here we can see the reference standards that we use for this system. These are 10K dbar parascientific transducers, as well as a parascientific transmitter that we use for QA check and for the readouts here on the monitor that you can see here. So that basically summarizes the entire cycle here with the pressure calibrations, which obviously we use pressure data in order to derive depth, which is possibly the piece of data that most oceanographers are interested in. And yeah, that basically summarizes that. So at this stage, I think we're ready to go to the last step of the process.
Yeah, absolutely. Just before we move on, we've got a few tanks here. How big an instrument can we put into these tanks?
So this, the internal diameter of this tank, I believe, is about 10 inches. I would have to confirm, Rob, on the diameters on the other tanks, but they're obviously smaller.
Yeah.
But we can fit in full concertos, full virtuosos. Maestros, we don't. We do those in a calibration body, and then they get fit into the final body. When we have these tanks, so this is a relatively new tank, so now we are able to do the Maestro in this tank. And obviously, when we're talking about floats, those do get pressure calibrated in a calibration body.
Float heads.
And then they get transferred, to the actual float head.
Excellent. All right, that sounds great. Okay, well, let's go over and have a look at conductivity then.
All right.
So that's for the temperature. We do get requests once in a while for specific temperature ranges, calibration over specific ranges, extended ranges. How do we handle that?
Yeah, so we usually treat those on a case-by-case basis because it depends actually on the specific requirement that the customer makes and if that's within our scope or not. But we do cover custom calibrations, and a typical example of that would be a customer that wants to extend the upper range from 35, let's say, to 38 or 40 degrees. So we have had cases in the past where we have customer requesting that, and we are able to provide those calibrations.
Nice.
Along with the data on the certificate as well.
That's excellent. Okay, so conductivity is next. There's a lot to cover here.
A lot, yes.
So
yes.
this will be fun.
So for conductivity, I'm actually going to pass it on over to our resident expert in conductivity. So I'd like to present Igor Shvorets, who's been with RBR for over 20 years. So he's one of the founding fathers of the company, and Igor hails from Ukraine and has a background in oceanography and metrology as well, all the way from his days back in Ukraine. So I will let Igor take you guys through the entire conductivity process, and then Rob will take it.
Yeah, sounds good. Are we able to shut off the pump?
Yeah, thank you. I'm in the middle of measurement, but
So we've hit Igor at the perfect time. He's right in the middle of the measurement.
Yeah.
So,
so let's me add some salt to our conversation. So we now in a what we call selenometry corner, and that's where all standards come in salinity or conductivity measurements. So that's from that bottle, which we purchasing from a company which located in UK, and the only one company in the world which know how to sell that standard. It's called IAPSA Standard Seawater, and IAPSA state from International Association Science, Physical Science of Ocean, and for 120 years, this service provide oceanographers with this standard. So actually it's natural Atlantic seawater, which was taken in Gulf of Biscay at depths about 100 meters and very well filtered and diluted to very close to salinity certified water. And after it's calibrated against potassium chloride according to the practical salinity scale, which established in oceanography since 1978. And I'm very proud that the big part of that development of practical salinity scale, which all oceanographers use for many than 50 years, and in developing of this industrial standard of salinity measurements called turbine ultrasol 8400B, which I was just operating. All these developments were happened in Ottawa, in our place, in a National Research Council, and this big man, engineer and scientist in Dauphiny, which I was lucky to be personal communicating and having some good relation. So that machine compare our samples, which were taken from our conductivity bus. We'll move soon to that place and compare it to standard to achieve the best accuracy in salinity measurement. But when we're talking about conductivity calibration, we need to understand that the practical salinity, it's a derivation parameter. So a practical salinity, according to practical salinity scale, derived from conductivity, temperature, and pressure. So this is why when we move around from each stage of calibration, from temperature to pressure, and now it's come to us for conductivity calibration, we knew that our instrument calibrated to temperature and pressure, and we use that data to convert salinity data from samples to conductivity data as our reference for conductivity calibration. And that process goes smooth against salinity, actually, salinity standard. And this is why it's very important to maintain high accuracy in temperature and in pressure too, to some extent, to know your best accuracy in conductivity. So now we move to our little oceans, what we have here. So it's conductivity bars. We have two, one set to 15 degrees and salinity 35. And we maintain it very precisely close to 35 to salinity of standard seawater. So it never exceeds more than that value. And we keeping that at 15 degrees, just having two wines with a water jacket, and you can see instrument deployed for calibration. It's well enough sealed inside and has no any metal parts. And that's primary calibration point. And we keep 15 degrees calibration for one reason, because practical salinity scale built at 15 degrees too, and standardization of standard seawater happened at 15 degrees too. So all standard condition of measurements of in a conductivity conversion to salinity based on 15 degrees, which is mean value of temperature in the ocean, and it's well distributed in the temperature scale. So second bus is more simply it's keep 25 around 25 degrees temperature, not need any stabilization. That's one of also servicing instrument in, and it just pumping and running again close to 35 salinity, and we carefully monitor state of salinity in the bus on our electronic notebook, and after use it for practical calibration in a bus. So 10 degrees step change give us number of temperature correction of cell geometry for 10 degrees step change, which is our temperature dependence correction. Cell linearity, one of advantage of our conductivity channel, that it's a linear by design. So many conductive cells which used in the practical oceanography as a company instrument has very nonlinear cubic or even more level of nonlinearity, and it makes it very difficult to calibrate because you need to perform very complex system to monitor temperature and salinity to make multi-points. And we have linear and our advantage in inductive cells that we can easily check linearity of that channel with doing simply, not very simple, but very efficient resistance test. So you can see at, I would say, climatizing cabinet, which set again to 15 degrees, and that another chamber where we set 15 degrees temperature. When we run resistance, what's called resistance test. There's some device called resistance box. We set up very precisely measured and accurately measured resistance. I can show you one on a bench, and it has resistance hook, which could be passed through the inductive cell, and set of resistors could modulate conductance input on an inductivity cell. And after, when we get that data, we can check linearity of response of conductivity channel to input conductance. That gives us understanding on performance in a range and in how perfectly electronics behave in a changing input of conductance. And after finishing that process, so we submerge instruments in a conductivity bus and measure what we actually estimate what called cell constant. So constant conductance from resistance box to conductivity in a seawater environment. And that's part of our process right here. But through it, all conductivity calibration happen even on the stage of temperature calibration when we investigate and correct offset temperature dependence. And even in the pressure sector, when we evaluate performance of conductivity cell assembly and all variation which associated with pressure effect. For example, we have here, we just removed, it's called saltwater bladder. That has name, which has been made. So that device, it has saltwater inside, and after instrument deployed and scope, we keep it in the cold state as in the ocean, and it goes to 2000 decibel pressure tank, and we modulate, it's pumped, and we modulate condition in the real ocean, how cell behave under changing of pressure. And we even correct that effect. So for many instruments, like for RBR project for 2000 cells, we correct that effect of pressure effect, which probably only we company could do it in a laboratory condition. Mostly oceanographers or instrumental designers do it at sea with taking samples from the bottle samples and correcting data in the real world. But we can do it in a laboratory condition. And that's one of our know-how, what we do here. So that's it. So we correct conductivity channel to temperature and to pressure do with even with some special equipment.
That's excellent. Well, thanks a lot, Igor. Really appreciate it. That's really
You're welcome.
comprehensive. That was great. Okay, so think of Ariel again. So that's excellent. So we've been through T calibration, which we call TCal internally. We've been through pressure calibration. And Igor did a great job explaining how actually each component is so critical to determining salinity to a high accuracy. And at the end of the day, it all ties back to the gold standard in that one as well. It's very, very interesting. Great. So now we're going to go on to the last part of the process. And for that, we're going to go talk to Mark. So we'll leave you here
All right.
and head out there. All right, let's go. So we're just heading back over here to the service area. We're gonna rejoin Mark Stacy here. Hey, we're already in the middle of something, I guess.
It's okay.
So Mark, so we just went through the whole calibration process with Ariel.
Mhm.
Igor gave us a great description of how conductivity is determined in reference to a gold standard water sample. Now, so what happens after all of that takes place? You receive the instrument
Yeah,
back.
that's right. We get the instrument back with the kind of the, I guess, the second to last stage in the process. The instrument will come out of the lab and come back in for final test. Now, final test is when we connect the instrument back up to Ruskin. We check the calibration coefficients that are on the printed certificate, match the coefficients that are in Ruskin. So the instrument, we know it's going to work properly. It's up to spec. We'll put new batteries in. We'll put the desiccant in. Check all of the O-rings. Really do that extra final check to make sure everything hangs together. Put the instrument back together exactly the same way that it arrived here in the factory in the first place, and get it ready to go to ship.
Well, that's a good point. I mean, we get instruments come in cages with
That's right.
all sorts of other sensors
Yeah.
connected to them. I think we had one.
Yeah, there was one.
Yeah, okay, so so there's a fair amount of work to get that all taken apart,
Yeah.
and then it comes back together again. Things can happen
That's
in
right.
the whole process. So we stop, we make sure everything's set, make sure everything works properly. And customers can expect they're gonna, when they get their instrument back as well, they got new batteries, they have fresh desiccant,
Yeah.
and so it's ready to go.
It's absolutely plug and play once the instrument comes right. I mean, unless you need batteries out of the instrument for shipping,
Yeah,
for government regulations, whatever that happens to be, really when the instrument gets back to you, it's really ready to go.
excellent. No, that sounds great. Now, a couple of things that come up. Someone inherits an instrument or it doesn't know the history of it. How do they find out when it needs to be calibrated? We
Right.
get that question quite a bit.
Yeah, we do. So when your instrument is connected to Ruskin, if it needs a calibration, if it's been over a year since the last calibration, there'll be a little orange triangle on one of the tabs in Ruskin. You can download the calibration certificates from Ruskin as well, from the information tab. And if you can't do that, like say if you've inherited it, you're at the field, whatever that happens to be, you don't have conductivity, you can always get hold of the support team here at RBR. We'd be more than happy to print out the final calibration certificates and send them over by email.
That was going to be my next question. Sometimes people lose cal certificates, they need them, whatever the case may be. They can just get in touch with you.
Definitely.
Take care of that.
Absolutely.
Okay, amazing. That's great. And then after that's done, we box everything up and it ships out.
That's right.
And so from the time, standard calibrations, from the time it hits our dock to the time it hits our dock to go out, 3 weeks or less.
3 weeks.
Excellent. Okay, that's great. That takes a lot of the concern out of
That's right.
it.
I mean, that means you've got an instrument that's ready to go. You've invested in the instrument. Now you've invested in the very best data that you can get.
Excellent. Well, thanks very much, Mark. Really
No problem.
appreciate it. So there you have it. That's a quick trip through our process. Again, we've just launched the 3 or 3 calibration turnaround guarantee. So we thought it would be really interesting to revisit. The Cal Lab tours are one of our most popular events. So we wanted to extend that a little bit, give people an impression of what happens on the front and back end of the calibration. Hopefully you had a chance to see that today. Again, we covered a few of the questions that had come up in chat. as we've walked through. But if you didn't get your questions answered, then what we're going to do is we'll consolidate them and we'll make sure you get your specific answer, even if it's something that is very specific to your situation. We'll get in touch with you directly. And then we'll curate some of the questions together and send that in an email after in the next couple of days. And you get a chance to see what other people are asking about as well, which will be interesting. Now, if you need help or if you need more information, you can always go to our website, rbr-global.com, and you'll find answers to any questions you need there. To learn more about 3 or free, the guarantee, or to actually schedule a calibration, you can go to rbr-global.com and /3-or-free, and that'll bring you right to a page where you can sign up for a calibration or book a calibration. And if you just need general help or support, you can get in touch with Mark's team at support@rbr-global.com. And those are the ways to get in touch with us. So don't forget, annual calibration is important. Plan for it. And we're trying to make it easier by making it as short a turnaround as possible. Appreciate the time. Thanks for joining us. And we'll talk to you again really soon. Thank you.